I guess like half of the audience already heard the talk, so it'll be almost the same. It'll be about the same topic, almost the same talk that I gave the last class workshop, but maybe a little bit more details because we have more time. So the topic is about trick-cut width. It's a width measure of a graph. It's relatively new, like 2 years old, and I'm going to introduce this notion, trick-cut width, and the relevant decomposition, and how to compute it approximately, and how you can use the information that a graph has small trick-cut width to design a good, efficient algorithm. So this notion, trick-cut width, was proposed by Paul Holland, 2013. So introducing the notion will be like one part of the talk. And I'm going to show the algorithmic application of trick-cut width. And this is based on joint work last year with Robert Gagne and Stefan Zeider from Vienna Technical University. And another part of the talk is to show how to construct a trick-cut decomposition of desired width value. And so in order to use a trick-cut decomposition, you need to first construct it. And because this notion is relatively new, the construction algorithm, no construction algorithm is known, no constructive algorithm is known. And this is based on joint work with Sang-Ilom, Christophe Paul, Ignacy Sao, and Dimitris Tilikos. And actually this work is not about trick-cut decomposition itself, but it's about some family of graph partitioning problem, and we could construct trick-cut decomposition by applying algorithm for graph partitioning problems. So let me first introduce some definitions. So immersion. So I just introduced immersion, but it's not directly relevant to understand the definition of trick-cut width and trick-cut decomposition. But it's good to know because it's a useful graph operation. And immersion is related to trick-cut width in the way that minor is related to tree width. So what is immersion? We say that H is immersed in G, or H is an immersion in G, if H can be obtained from G by a sequence of vertex deletion, edge deletion, or lifting a pair of edges. So you know vertex deletion and edge deletion. And what is lifting of a pair of edges? When there is a pair of edges which share one common endpoint, we delete these two edges and make these distinct endpoints by an edge. This is what is called lifting. And an equivalent definition is that if there is a mapping pi from the vertices of H and edges of H to the graph G, such that for every vertex of H, pi maps the vertex of H into a vertex of G, and the images of these vertices should be all distinct. For every edge of H, the image of pi should be a path in G, such that the endpoints of this path should be the images of the endpoints of the endpoints of the edge. Okay. So if this is H and this is G, and if H looks like this, then the images of these vertices of H in G should be all distinct. So it's like this. And for every edge in H is mapped to a path of G. And the endpoint of the path is the image of the endpoints of the corresponding edge. So it's okay. Let's compare it with the subdivision. So K4 as a subdivision, so you can consider it as a graph where you forget some subdividing edges. So subdivision looks like this. So the path that connects the images of the vertices of H should be all vertex disjoint. In contrast, K4 as an immersion, again the images of the edges of H are paths. So between these, these big blue vertices are the images of vertices of K4, and between two vertices, so every two vertices are connected by a path. So between these two you have a path, between these two you have a path, between these two you have a path, and so on. So while in the subdivision they should be all vertex disjoint, in the immersion it doesn't need to be vertex disjoint, but they should be edge disjoint. So why is immersion interesting? So immersion is another relation such that graphs are weakly quasi-ordered. Well quasi-ordered. Well quasi-ordered under that that relation. So that graphs are well quasi-ordered under weak immersion. Okay, forget about what weak means, but it's under immersion in the way that I introduced. It was conjectured some time ago, and it was rather recently proved. And you have some analogous phenomena going on between the world of immersion and grid in the world of minor. So for example, the monumental theorem in graph minor theory is that if the tree width of G is big, then you can find a big wall as a subdivision. And you can make almost the same statement by replacing tree width by tree-cut width and subdivision by immersion. So tree-cut width, this notion tree-cut width was designed so as to facilitate such a statement. That's one of the motivation to introduce tree-cut width. So okay, so here comes the definition. So the definition of decomposition itself is very simple. Given a graph, the tree-cut decomposition of G, the given graph G, is a pair of two objects. One is a tree, another is a set of vertices associated to each node of the tree. So it's like, if you know the definition of tree width, it's the same pair. And the difference from tree width is that chi is the collection of vertex sets associated to each tree node. They should form a partition of the vertices of G. And I say that it's near partition because we allow empty set. So some of these xt can be actually empty. Yeah, so another way to understand it is given a tree T, so tree-cut decomposition is a mapping from G to tree T. So this is chi can be understood as a mapping from the vertices of G to the node of the tree. So every vertex will be mapped to some node, and some node will get no vertex, so it can be empty. So the nodes, the vertices which are mapped to a specific node will form a partition of V of G. Right? So until this point it's simple. So when you have a decomposition, you want to have a you want to have a measure to you want to measure how good the decomposition is. So so this is called the tricot width, and to the tricot width is measured with it reflects two aspects of this decomposition t chi. So one is a cut size, which is a number associated to each edge of the tree. Another is what I call the size of the torso, which is associated to the node of the tree. So what is a cut? So this blue thing is a tree decomposition, and I didn't draw the vertices of V of G, but you can imagine that they are hidden. So pick an edge E of the tree, and I define the cut of E as the set of edges with one endpoint in Y of V and another endpoint in VG of Y of V. And what is Y of V? So let U and V be the endpoints of E, and you can consider the union of all the bags on one part of the subtree, and you can consider the union of bags of the other part of the subtree. And this will form a bipartition of the V of G. And cut of E is exactly the edges of G, such that one endpoint is here, another endpoint is here. Okay? So you can imagine that you want to count, you want to make the size of the cut of E as small as possible for every edge of the tree. So this is one measure you want to reduce. Another measure you want to reduce, so is the torso size at a node T. Okay, so so the definition of torso size is a bit tricky, so I try to simplify it as much as possible whenever I give a presentation, so I change this slightly, but still it may be a bit strange. Okay, so suppose that G is a three edge connected graph. Yeah, actually there was a small mistake in the presentation that I gave in KIAS. Yeah, well, it's almost true, but when it's three edge connected. So yeah, so suppose that graph is three edge connected, then torso size. So so when it's three edge connected, what do we know? We know that for every edge E of the tree, the cut size of E is at most, it should be at least 3, right? So if you have cut size 2 here, then this corresponds to the cut of size at most 2 in the graph G, which contradicts the 3 edge connectedness. So for every edge of the tree, it should be at least 3. And for node T, the size of torso is exactly the sum of the size of the back xt and the number of neighbors of T.
When you count number of neighbors, these are
neighbors in T, in the tree. Yes, in the tree. Yeah, all neighboring tree nodes of T. So yeah, it's simple. So for every tree node, I count the number of vertices in the back of T, and I count the number of neighboring nodes of T. That's another measure that I care to measure the tree cut width. So again, when the so these are two measures that we care, and the width of a tree cut decomposition when the underlying graph is 3 edge connected is the maximum of the cut size over all the 3 edges, and the maximum of the torso size over all the 3 nodes. Okay, and of course the tree cut width of the graph is the minimum of the width of all such decomposition. Then the question is, what about the general case when the graph is not 3 edge connected? Then I look at every maximal 3 edge connected graph, and so this will decompose the graph into. Okay, I'll show you how it's very easy to obtain a partition of the graph such that each part is maximal 3 edge connected graph, and then for the tree cut width of width of the graph is maximum of the tree cut width of each of these induced subgraph. And how can you decompose the graph into such a thing? So if the graph is 3 edge connected, then I have nothing to do. I just feed G as G1 there. If it's not 3 edge connected, then I find a 2 cut like this, and if this is not 3 connected again, then I again find another 2 cut. And if this is not 3 edge connected again, then I find another 2 cut, and so on and so forth. And suppose that this graph so let T1 chi1 be a tree cut decomposition of this part, which was obtained recursively.
So those are subgraphs, right? GI is maximal 3 edge connected.
Yes. So T2 chi2 T1 chi1. Then I will obtain. So we obtain a tree T by taking the union of T1 and T2 and adding an edge between one node in T1 and another node in T2 in an arbitrary manner. Okay, so let's say T1 is like this and T2 is like this, and the chi1 forms a bipartition of chi1 forms partition of G1, V of G1, and chi2 forms a partition of V of G2. And to obtain a tree cut decomposition of the entire graph, what we do is I simply put T1 and T2, both tree decomposition, into one place and add an edge like this. Then the tree cut width of this decomposition is maximum of these two. Okay. So you can do it recurrent. So you can obtain. So if this one is not 3 edge connected, you can do exactly the same thing and obtain the tree decomposition of G1 recursively in the same manner. So you can obtain tree decomposition for the entire graph.
Then what if the graph is too small?
What if the graph is too small?
Like just triangle.
Good question.
And the tree cut width of that triangle is 1. I don't know, 2.
Yes. So
How? This definition.
So this is not you cannot consider it as a definition. It's rather procedural way to obtain a trick or decomposition. I avoided to give a real definition because it's really shitty.
Right.
But I think it's good. It's okay enough to have an overall intuition of how the width is defined. So the thing is that when you do it this way, it means that when there is a cutoff size at most 2, then even if you add an edge like this, it doesn't affect the size of the torso and the width of, the size of this cut on this edge is at most 2 anyway, so it doesn't increase the cut size of the entire graph. So in fact, the original definition of the torso size for a general graph is designed so that such a cut doesn't increase the size of the torso. Okay. Okay. So yeah. So this is an example of the torso size at each node and cut size at each edge, but I'll skip it. So this is a relation diagram with measures of graphs. So on top you have tree width. So okay, so we know that if path width is small, then tree width is small, right? And there is a notion called tree depth. So the graphs with small tree depths are graphs which have small path width and which doesn't have long path. So it has small path width, and this path decomposition doesn't have too many bags repeated in the how to say, doesn't have too many bags which are on the path. So cut width bounds the path width, and if you have small cut width, then the degree of the graph is bounded and the tree width is bounded. And tree cut width, so having small tree cut width is actually a generalization of having small degree and small tree width. So if a graph has small bounded degree and bounded tree width, then it has bounded tree cut width. And if you have a small tree cut width, and then the tree width is bounded. Okay, so do you know? Have you heard of path width? Do you know the definition? Yeah. So. So this is
tree width, but you use a path.
Yeah, so it's a tree width when the underlying tree is a path. Yes. So this is an example that path width and tree cut width are actually incomparable. So there is a graph which has constant path width and unbounded tree cut width, and vice versa. So full ternary tree of depth n. This is typically has, so it's tree width 1, but the path width is n, or I think it's n or n minus 1. But the tree cut width is 1. So every tree has tree cut width at most 1. Right? And this graph has tree cut width n and path width like 3. So why? Okay, this. So the second graph, it's obtained from star with n leaves by replacing each edge with n parallel edges and subdividing them. So this is n, and you have n leaves here. And why does this graph has path width, constant path width? Because you can have you can define back in this way. So put one back. So in the first back you put this vertex, this vertex, this vertex. In the second one you again put this vertex, but forget this one. You put this, 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 and the next one has this, this, this. So the backs will contain something like this. And when the back consumes all the subdividing nodes, then I forget this one and move to the next one. Right? This defines a path, and the center vertices appear in all the backs. And this will be path width almost 2. Okay. But it doesn't have trickled width. But the trickled width is n. Why? There is a very simple argument for that. But this is three-edge connected graph, so you can use this a bit cheating definition to argue that. Okay, so here I call z x1 x2. Okay, the argument is actually quite simple. So x1 and z, they should be in the same bag. Why? If they are not in the same bag, it means that you, okay, the claim is that the trickle width is bigger than n, right? If the trickle width is m of n minus 1, then it means that there is a so suppose that the trickle width is m of n minus 1, and these are not in the same bag, but the cut size here is n, right? So these two should be in the same bag, same bag, same bag, same bag. So they should, so this n plus 1 vertices should be in the same bag. So the torso size is already n plus 1. Right.
But you said this is three-edge connected, but this is not, right? Because of small degree vertex.
Ah, yes, you're right. Yeah. Yeah. So actually, you can define trickle width. Okay, you can get rid of this subdividing. So you can equally you can define trickle width on multigraph as well. So, yeah. Okay, so yeah. So can we? So the next question is, we have defined the trickled width, and having small trickled width, does it help to design efficient algorithm? So we know that having small tree width is good to design to have faster algorithm when the problem is intractable in general. So how about trickled decomposition? So well, before you actually start to design algorithm on small trickled width graphs, you need to know that this makes sense, right? Before you actually start to design an algorithm, if having such an algorithm is already implied by some other results, then it's worthless effort. So, and also we want to know for which problem it makes sense to design algorithm when the graph has small trickled width. So the first observation is that so when the trickled width is small, so this equation says that if the trickled width is small, the tree width is small. So consider this as a set of graphs which has bounded trickle width. Then the set of graphs which tree width, and the set of graphs which has bounded trickle width is actually more restricted. Okay, you cannot, yeah, it's more restricted. So if some problem already can be solved efficiently on small tree width graphs, then you don't need to try to make an algorithm on this part of the graph. You can just use that algorithm that works on small tree width graphs to solve a problem that belongs to here. So what you need to design is for problems which is difficult on small tree width graphs. So that's what we actually look at. So these are list of problems. So we know that there are many problems which become tractable when it's hard in general, but it becomes tractable when the tree is small. But also these are examples which are still intractable on small trees graph. Yeah, so it's hard. You don't need to understand what the blue one means. And our result is that while the problem may be hard on these instances, it may become tractable on these instances. For the first three problems: capacitated vertex cover, capacitated dominating set, and imbalance. And also there are some examples which is again hard on these more restricted graph classes. So it means that this width really it's different from tree width, right? In the behavior of in the algorithmic behavior. Yeah, and also, okay, if you look at the third column, they are all, so FUT means that they are tractable. They are all tractable. It should be this way because if you have bounded max degree and bounded tree width, then these are graph classes which are like this. So if some graph classes, for some problem, if this such instance is again hard, then it should be hard on these kind of instances. So you don't need to look at, it's worthless to try to design an algorithm, right? So we design dynamic programming algorithm that works with tree cut decomposition, which is rooted. And so I think you know of dynamic programming algorithm, right? So I assume that you know at least one dynamic programming algorithm. So like other dynamic programming algorithm which works on tree decomposition. So we consider rooted tree like this. So this is a root. Root is somewhere up. And the principle is that when you have partial solution on the subgraph induced by some subtree here, and when you have partial solutions on the graph induced on this partial subtree here, you use these partial solutions or encoding of the partial solutions to obtain partial solutions for the subgraph induced on this subtree. So you use the information of partial solutions on its child to use to compute the partial solutions on this node. So starting from the leaf, you can compute partial solutions, and you can use the information in the tree node, which is more closer to the root, and you can repeat it. Then you will eventually have information of partial solutions at the root, which is actually a solution for the entire graph. So, and this is the general approach to design dynamic program algorithm with using tree structure. And we do the same thing, basically. So what you need to know is that what partial solutions you need to have, and how to use the partial solution, and how to encode the partial solutions, and how to use the partial this encoding of partial solutions at the child to obtain the encodings of partial solutions in the tree node. Right? Yeah. Well. Yeah. So, and before you do this, it's better to, how to say, make the tree decomposition in a neat way, to present it in a neat way. So that's the first thing you need to do. And in the later you will see that this is actually quite crucial to design dynamic programming algorithm. So this is rooted, and I look at the tree node T. Then what? So this is not an algorithm for problem on the graph, but it's just pre-processing to make the decomposition in a neat way. Right? So I first classify the node into two things. One is AT and another is BT. And what is AT? It's the children of T such that the cut size on this edge is bigger than 2, or the cut T means the cut edge between this node and the rest of the vertex set. The cut T contains an edge with one endpoint here and another endpoint in the back above T. Not T, or not somewhere here and not somewhere here, but somewhere here. So whenever a child satisfies one of these two properties, then I will classify it as AT, and all the rest will go to BT. Then, okay, so the first observation is that the number of children in AT are bounded by K. Do you see why? There's more hint. The number of children in AT is at most 2K. If the tree width is at most K. So the number of children which satisfies the first criteria should be at most K. Why? Because of the torso size at T. So the torso size at T is the sum of vertex set here and the number of children that satisfies this criteria, right? So you should be at most K. And the number of children that satisfies the second criteria should be at most K because of the cut size here. So suppose that if this child sends one edge to a back above T, then this edge will be counted as a cut between this node and this node, right? This edge. And the cut size here should be at most K. So there should be at most K vertices which actually has an edge whose endpoint is above T. So the number of such children should be at most K. So here you have at most 2K vertices, which is very good to enumerate all partial solutions. That affects what happens here, right? But the number of children at BT can be arbitrarily large because the cut size that's counted along this edge is at most 2, and they don't affect the size of torso at T. So you can have 1 million children here. And this actually produces the difficulty of enumerating all possible partial solutions, all possible solution behavior at T. So if here the number of children is bounded, so you can basically enumerate whatever you like. But here it's too many, so you cannot do that. And the pre-processing is to settle this situation. So how do we settle the situation? So we do pre-processing, which works in polynomial time algorithm, so that for every edges which are between the children here and somewhere outside should be actually landing exactly at back in T.
I mean, this is how. I mean, this is. I mean, you
Yeah, this is
modify the tree.
Yeah, we modify the tree so that it will satisfy eventually that property. So at the beginning, it doesn't satisfy this property. So it can, for example, it can look like this. Oh no. Okay. Yeah. So at the beginning, the edges between BT and the rest of the graph can be anything. So they can be like this. So the other endpoint can be in back at T, but it can be also landing here. It can go between two children in BT. It can go anywhere. Of course, we do not go to here, because if it sends something here, then it should be classified in AT. So it can be messy. And actually these such edges make the computing of dynamic programming quite difficult, right? And our goal is to get rid of such thing. So we don't want to have an edge that goes like this or this, but we want that everything goes the other endpoint of all these edges landing exactly at back at T.
Are you going to explain it, or are you just going to assume that this is...
No, so the claim is that there is a polynomial algorithm which like transforms the tree so that the obtained tree satisfies this property, and the width is exactly the same. Yeah. So well, actually it's not magic. So when there is an edge that is like this, the crucial observation is the cost size between the back here and the rest is 2. So actually you can move it to somewhere else. Move meaning that you remove this tree edge and connect it to somewhere else. This doesn't change the tree cut width. So you move this tree node, which creates this messiness, so that it doesn't create the messiness. And if you do it in a nice orderly way, then you can get to this situation. Okay, so we obtain this picture. So AT has this property, and they have almost 2k children. And BT, there can be arbitrarily many nodes, but they have this nice picture that the cost size along each tree edge is almost 2, and the endpoints of this cut edge is lands in exactly at xt. Okay, so well, I exemplified with capacitated dominating set, but I'll not give you the detail. Once you understand the definition, then it works how you can imagine. So basically, so because here at AT you have bounded children, and also for each children, for each vertices that are induced by this subtree, the vertices which interact with the rest should be most k, because the cos size along this edge is most k. The vertices which touches the rest of the world should be most k. And actually, these are the only vertices you need to take care of when you compute the partial solutions at T. So you have k vertices that you need to take care, k vertices, and at most 2 k square vertices that affects the behavior of the solution here. And so you can enumerate whatever you like. I'll not give you the I'll not go for detail, but you can actually do it yourself. It's complex but not difficult. So it boils down to the case when AT is empty, because you have enumerated all possible behavior of XT with AT children. So suppose that you have enumerated all these possibilities and you have taken these phenomena into account to the state of XT. So this is what remains. But the problem is that you have 1 million children here. So the crucial observation here is that all the edges, so you have exactly all the edges land in exactly XT. So you can classify the nodes in BT so that you can group them so that each group has exactly the same neighborhood in XT. You have k choose 2 plus k plus 1 possible way of having neighborhoods in XT. So you have that many groups in BT. And okay.
But some of the vertices in XT are like probably colored because of situation in AT.
Yeah. Yes.
And more situation.
Yes. Yeah. That's it's a good point. Yeah. Okay. So the first. Okay. Let's do it step by step. So each node has finite state. What does it mean, finite state? It means that the state is the encoding of partial solutions for the induced subgraph here. So each node has finite state. Because why is it? Basically, it's because you have only 2 boundaries. You have constant number of boundaries, and you have only constant number of states that these boundaries can be involved in the partial solution. Like this one is dominating set, or this one is not dominating set, but dominated by some vertices here, or this vertex is dominated by someone else here. It should be dominated to someone else here. So there may be many states, but they are only finite, and because you have only 2 boundary, the partial solution description at the boundary is constant. That's what this finite state means. So the first try is that I consider every possible. So suppose you have C possible states here, C possible states here, C possible states here. So the first try is to consider C to the 1 million different ways of combining states from each children to compute the enumerate all partial solutions at T. But it's too many. It's C to the 1 million. So we want to avoid C to the 1 million, but do something else. So that's where this grouping comes from. So one group are these nodes which share exactly the same neighborhoods in XT, and which share exactly the same table of states. Okay, but you can just, I don't define what this means, but it means that they how to say? So if you have C states here, if you have C states here, then you can have one-to-one correspondence between these 2 states. So what happens here can be exactly translated to what happens here. And, okay, but you have a feel of what it means. And because you have finite states at each node, and there are finite way of having neighborhoods in XT, the grouping is finite. Is actually a very small number. It's O of k square, I think. And then all these nodes in one group behaves exactly the same way. So if the partial solution, including xt and everyone here, uses certain state here, state 1 here and state 2 here in the same group, then you can actually exchange it. Instead, you can describe exactly the same partial solution using state 2 here and state 1 here. So you don't need to look at individual nodes, but you can formulate it as a number problem, which is integer linear programming. Okay. Okay. So this is basically the idea for dynamic programming, and I'll move to the next topic if
here the number variable is like the number of groups that you
yes.
Since this is bounded, you can
so number of groups, yes, so the number of variables, I think I don't remember exactly. The number of variables is the number of groups plus times the number of states in each children, I think. And so you can formulate the problem in ILP, and ILP can be solved in FPT with respect to the number of variables. And the number of variables is like O of k square. Okay, so this dynamic programming will work only when you're given a tree-cut decomposition. So I'll give a brief overview how to compute the decomposition. So if you want to exactly compute the decomposition, then the quest is to design an algorithm which answers the question exactly. So either produce a tree-cut decomposition of width and most k, or correctly declare that the tree-cut width is bigger than k. And the quicker the better. And this problem is a little bit hard, so we relaxed the requirement a little. So instead of answering the question exactly, we answer the question approximately. So either produce a tree-cut decomposition of width and most 2k, or declare that the tree-cut width is bigger than k correctly. So if the tree-cut width is like 1.5k, then depending on how the algorithm works, the algorithm may actually produce width and most 2k decomposition, or it may just say no. So both things can happen. And because of this fuzziness, it's not the exact algorithm, it's approximate algorithm. But this algorithm guarantees that if the tree-cut width is smaller than k, then surely you will have decomposition of width and most 2k. So how does the algorithm work? We start with a random cut, which induces this bipartition A and B, and say that the cut size is most 2k. Such a cut can be found in polynomial time. You just use a min cut algorithm. So we start with an arbitrary cut, and we consider this cut and bipartition. We associate it with a tree-cut decomposition that looks like this. It consists of one edge with two endpoints, and the back of one endpoint is A, vertex set A, another one is B. This is certainly a tree-cut decomposition, right? Only that the width is not at most 2k. The width can be very bad because you have a lot of vertices here and here, but it's a tree-cut decomposition. And the idea is to grow this tree bigger and bigger. And while you grow the tree, the size of the back will decrease and decrease until, and throughout the whole process, the cut size at each tree node will be at most 2k. So here is at most 2k. Through the whole process, we keep a tree cut decomposition such that the cut size is at most 2k, and the back size can be arbitrarily big, but we will grow it and the back size will decrease until the width size, the tree cut width is at most 2k, or you have a certification that the width is bigger than k. So actually the algorithm produces a certificate that the tree cut width is bigger than k. So how do you do that? So from the previous picture, we want to move to this picture, which corresponds to the decomposition that looks like this. So what's yeah? So how do we refine this A into A0, 1, 2, 3? By obtaining, because this A0, 1, 2, 3 forms a partition, we need to find a partition of A. And we want to have that the back size decreases, it's non-degenerate, and also the cut size should be at most 2k. The partition should satisfy some criteria, right? And what criteria do you want to satisfy? So is these three. So we want to find the partition of A such that between A1 and A0, A1 and the rest, A2 and the rest, and A3 and the rest, the cut size is at most k. I didn't write 0 here. So between A0 and the rest, the cut size doesn't need to be at most k. Okay. And the cut size between A3 and B is at most k. A2 and B is at most k. A1, B is at most k. Yeah, you can say A0 and B is at most k. But this, yeah. And another requirement is that the number of parts, should be at most k. So actually this number k is not exactly k. If you really want to solve the problem, it should be there should be a little modification, but that's basically it. So why do we need this kind of requirement? So the first one, this is to satisfy the cut size of the tree cut decomposition. So if there is a tree cut decomposition of width at most k, then there is a tree cut decomposition of width k of the graph induced on A. And yeah, so you can actually find some back and its neighboring partition such that the cut along this edge should be at most k. And this one will actually detect such a partition. And why do we need this second condition? So we need this second condition because we want to do recursion. So we want that the tree cut width of the overall graph should be at most 2k. No, we want that the cut size of the overall tree decomposition is at most 2k. And if you have cut between A3 and this rest is at most k, and if you have cut size between A3 and B is at most k, then between A3 and the rest is at most 2k. Right? And this number of parts is to ensure that the torso size is at most k. So you can imagine that it shouldn't be actually exactly k, but it's like k minus the size of A0 and something like that.
Yeah, but you have to worry about the cut size too.
So
did you pre-process?
Yeah. So the thing is, we do this algorithm of 3H connected graph, So we first find we take care of this size 2 edge cut, and we combine it later as I explained before. Yeah. So this problem, and actually the second condition, so taking care of the cut between AI and B, this condition is a little bit bad because we want to forget about these B vertices. We want to solve some problem. We want to find the partition of A, and when you do that, you want to forget about B vertices. So we reformulate this part by the requirement that each part AI should have at most K terminals, and these terminals will correspond to the endpoints that cross B and A. Okay. So this becomes kind of a partitioning problem with terminals. And we solve this problem by applying algorithm for more general graph partitioning problem, and which works in this way, which is Okay, so I exceeded by 1 minute. Thanks.